Hi, everyone. Um, my name is Mike Cohen, and today I'd like to introduce to you a tool, a DFIR tool called Velociraptor. You may have heard of Velociraptor. It's been around for a couple of years now, and uh, it's recently become much more popular through the DFIR community because it has some very unique abilities and it's very flexible. And the main reason for that is that Velociraptor uses something called the Velociraptor Query Language, or VQL. And in Velociraptor, VQL is actually used to drive everything, including information from endpoints, monitoring for response, monitoring and response on endpoints, and controlling and managing the Velociraptor server. So this is only a very quick talk. We're not going to really go into a huge amount of detail about all the capabilities that Velociraptor has. But I'd just like to give you a quick overview of Velociraptor and how it actually is deployed in practice. Typically, we deploy Velociraptor in a server, the Velociraptor server in the cloud, and then we have a whole bunch of assets, which are laptops, desktops, servers. So the assets are the endpoints that Velociraptor monitors, and we call them in Velociraptor terminology the clients. And the clients communicate with the server using a persistent communication channel. This persistent channel allows us to task endpoints very quickly, so we don't have to wait for polling or anything like that. And then we will have the admin UI, which is a web-based UI that we use to control the Velociraptor server. And we're going to see that. We're going to do a little bit of a demo later and work through a scenario just to give you guys a bit of an idea as to how to use Velociraptor, how it can be useful in a real world. Typically, Velociraptor servers are very scalable. We can easily run to 10, 20, 30,000 endpoints because the server actually is very efficient. It doesn't do all that much. It just simply sends the VQL query to the endpoints, and then the query is actually the thing that collects all the data. So the endpoints are doing all the heavy lifting and simply sending back the results of the query. And we have a client memory and CPU usage, throttling and control, so we can make sure that we don't have too much overload on the endpoint. But as far as the server is concerned, the server is actually just designed to just accept those result sets from the endpoints and simply store them. So this is the reason why it's actually very scalable, and it's not unusual to have 20, 30,000 endpoint Velociraptor network and be able to query endpoints in seconds. So just to work, we don't really have time to go through all the features that Velociraptor offers, but I just thought that I'll just go through a very common type of DFIR investigation. I was reading my Twitter feed the other day and realized and noticed this new vulnerability was released, was announced in the Dell driver, the Dell kernel driver. Now, this was probably a few days ago, so it's actually very, very recent, very pertinent. So this is the CVE that was released, and you can read this advisory that was released by Sentinel Labs, which is kind of a very interesting kind of advisory. It turns out that an old sign driver produced by Dell was highly vulnerable to multiple types of attacks. Now, when a driver is vulnerable, it's actually quite dangerous because it allows people to essentially inject code into ring 0, into kernel mode, because they can bypass a lot of the security mechanisms that the Windows kernel implements. So this is actually kind of a big deal. You can read all about the details of the vulnerability, but just to give you an idea, hundreds of millions of Dell computers are at risk because of this vulnerability. So what is it actually all about? I then went to the Dell website and had a look at the advisory from Dell, and it basically talks about a driver called dbutil23.sys, which is a driver file, and that is the vulnerable driver that is causing the issue. How are we supposed to remediate this? Well, if you scroll a little bit down the page over here, here are the instructions. Well, we have to check the following locations for this dbutil23.sys driver file: users, username, app data, local temp, and C Windows temp. So this is okay if I only have to look at one or two machines, but if I have a fleet of about 10 or 20,000 endpoints, how do I actually do this in a fairly scalable way? How do I check that if those systems are compromised? So this is where Velociraptor shines. Velociraptor allows us to do something called hunting. So hunting is where you proactively go and search for vulnerabilities or issues in systems. And this is where Velociraptor really shines, because it's scalable and you can simply actively go and look for specific kinds of artifacts, forensic artifacts that are left on the endpoints. So we don't really have to then depend on receiving logs or collecting kind of telemetry or whatever. So in Velociraptor, the term hunting simply means that we are collecting the same kind of forensic artifact from many endpoints at the same time. So it's just a container for many different collections, and you can actually operate on all of the collections at the same time. And I think that the easiest way for me to show you how this works is through an example. So let me just switch to the Velociraptor console, which is here. So here I have a Velociraptor setup, and you can see in the welcome screen, this is the welcome screen. I'm just going to switch over to the dashboard here and show you that I have approximately 2,000 endpoints currently connected. Currently connected clients are around 2,000 endpoints, and the server is mostly idle. It's using 360 megs of RAM and maybe a quarter of a core. So it's mostly idle. If I click on the show all, I can see all the clients and interact with them individually. But in this case, what I want to do is I actually want to do a hunt, so I can collect the same kind of artifact everywhere. Now, if I go back to my advisory, which was over here, I need to check the following locations for the dbutil2.3sys driver. Okay, well, then I can use Velociraptor to do this. So I'm just going to create a new hunt, just like this. First thing I want to do when I create a hunt is give it a description. So I'm just going to check for dbutil hunt sys. And then the next step, I need to select which artifact I'm going to collect. And because I'm just trying to find files right now, I think the file finder is the easiest artifact to use. As you can see, this is an artifact called Windows Search File Finder. Now over here, I have a bit of an explanation of what this particular artifact does. It's basically just searches for files. And I have the opportunity to search based on a glob, apply some YARA rules, upload the file, calculate hash, and other things like that. Check by timestamp, filter by timestamps, and other things. But ultimately, underneath it all, it's simply a VQL query that is going to run. But I don't really need to look and understand the VQL query, but this is just how it's implemented. The next thing I need to do is just simply configure the parameters, which is the next screen along. And here I just basically have to put in the files to find. Now, if I go back to my advisory, then I'll just copy and paste it so I don't have to type as much. Then I'm simply looking for something like C users for all the users. So I've got a wildcard here, app data local temp dbutil.sys. So according to the advisory, if this file is present, then this system is vulnerable and I need to remediate it. So let me just also calculate the hash if I do find it. And that's basically it. I'm just configuring my my artifact, and I'm just going to launch it. Now, when I do this, this creates a hunt. So that means that all the currently connected systems will execute this, will collect this artifact when I click start. When I just created this hunt, it starts in the paused state, so it's not running right now. So I'm just going to click start, and off we go. So that will cause the artifact to start, and you can see immediately that endpoints are being scheduled, and immediately they're starting to run. Right. So all of these endpoints are searching for that particular file on the endpoint. Now, as the results are coming in, I can click that notebook here to essentially analyze the results as they're coming in and look at, the findings. Now, because this particular artifact will actually return no results if the file is not present, but it will return results if the file is present. So in this case, I only actually have one machine that is vulnerable, that has this dbutil driver. Even though I've examined 2,000 machines, I only have one machine that is vulnerable. So this is an example of a hunt. I've just run the hunt across my entire fleet, and 2,000 machines were clean, and one machine had that file in it. So now I know this one is the vulnerable one. And so this is how, in seconds, I can essentially triage my entire network to figure out exactly which machine is vulnerable. So let's continue on with this this scenario, and let me just point out to you the different kinds of things in the hunt. So over here we have the overview. So over here we have this thing which is the artifact. So an artifact is simply a query with some explanation around it, some kind of human readable description, and there's the query. So we've already seen it before. We can simply click on this to remind us of what is this doing. It's finding files and so on. You can see here that we have an expires time, and you can see that the hunt will expire in approximately a week. So by default, hunts are always active. So if another machine turns up in the next week, then it will automatically just receive the hunt and immediately start doing that hunt. So we can also see here that is the configuration of this collection. So we said search for this particular endpoint, search for this file on the endpoint, and calculate the hash. So this is basically what I selected in my options. Now over here, I can actually create a download and download all the data, but in this case, it's just the one hit. And the notebook is, again, where we can post-process this data. Okay, so so we can see that we found the hash. We found there was one result, and we had we have scanned 2,000 endpoints. Okay, so this is cool, but did we actually get owned, right? Because this is, this is where we would expect to find the driver naturally, if the machine is vulnerable. But did anyone actually exploit this to get into the kernel? Because a vulnerable driver is actually a really bad thing, because it allows people to escalate into a ring 0 type attack. So not only do we expect to see that if the driver happened to be there, someone might exploit it, but also it is entirely possible that if the machine is already compromised, that an attacker may bring the driver with them in order to allow them to get into kernel mode. So, so then the question is, is it possible that this file exists somewhere else on the disk in a different kind of location, different place. And that is actually kind of a problem, right? How do we scan all the files on the disk, all the file names on the disk to make sure that, that driver doesn't exist? And so one of the things that we can do is use Ntfs analysis. And that is a forensic technique that is used for being able to understand timestamps, to understand where the file system, how the file system is evolved to represent the files in the way that it does currently. Now, I'm not going to go into a huge amount of details at the moment about how Ntfs works. But the most important thing to get out of this is that Ntfs works by having a big master file table, which is just a big table of all the files and on the disk. So essentially, it gives us one place that we can find, we can quickly scan to find all the files on this volume. So here I have a picture of the MFT, and MFT simply looks like a bunch of MFT entries in a row. The file contents themselves obviously stored on the disk elsewhere, but we can easily scan the file's metadata to figure out the file names and timestamps and other things about it in a very efficient way. So Velociraptor has the ability to scan for Ntfs volumes, and it has the ability to do Mft analysis. So we don't really need to download the MFT off the machine. We can simply analyze it straight on the machine. And the way we do that is simply by using an the MFT artifact. So again, I'm going to do another hunt here, and I'm going to search for this file somewhere else on the disk, elsewhere. So let's say search for file using MFT. Okay, and so all I need to do, so whilst I need to kind of understand what the MFT roughly is, which you guys can understand that right now. I don't really need to know much more about it because I can simply rely on the fact that Velociraptor comes with an MFT parser and an MFT artifact. And this particular artifact allows me to scan all the files on the MFT and simply filter for the file names that I'm interested in. So I'm just selecting this artifact, then I'm configuring the parameters over here. And all I have to do is search for a particular file, which is called dbutil23.sys, right? That's the file that is interesting. And let me just search for that in all attached Ntfs drives, all the files, and then just see where can I find this. So again, I'm going to do a hunt, so which will operate on all the 2000 machines at once. Let's start it. Here we go. And immediately I'll get the machines being scheduled, and the hunt will kick off. Now, usually it takes about a couple of minutes to do this, to scan the MFT, but I'll only expect to get positive hits because I've already filtered it fairly heavily. Now, if you just collect the MFT artifact, this artifact by itself, then usually it returns something like 300,000 or 400,000 rows, because there are that many MFT entries, or possibly even more than that on any real system. But because we're doing the filtering itself on the endpoint, then what we're actually going to get are the positive hits. So what's coming back from the endpoint are only those positive hits that have that have those files there. So it should be maybe a couple of dozen, maybe one or two instances of this of this dbutil driver, and so it's still going to take maybe a couple of minutes to actually to find it. But then once it comes in, then there's not going to be a lot of data being transferred. And this is the reason why Velociraptor is so fast, because most of the processing is really done on the endpoint at this point. So each endpoint is simply looking at its MFT, and it's only going to scan, a couple of, it takes about a couple of minutes to actually do the scan. And so, the server itself is mostly idle, just waiting for those results to come in. And as the results come in, it basically just collects them. It's going to take a few seconds to have that going. Let's go back and yeah. So this is what the MFT looks like. So again, the same thing. We've basically just created another hunt, and we're collecting this new artifact. It's going to take a couple of minutes to have that go. Okay, should expect to see that coming back soon. Okay, here we go. So now we're starting to see some results coming back. And of course, the clients will finish at different times, and some will take longer and some will take less time, depending on how many files they've actually got. But you see those results are starting to come back now very quickly. So we can immediately have a look at the results here. And this is again the notebook. In the notebook, we are able to do post-processing or any kind of examination of the results. In this case, out of all our 2,000 machines that we have, we've only got 3 hits. Now, I can just, let me just turn off some of those columns that are not very important for this discussion, so that we can see, maybe we obviously get all the timestamps. There are many timestamps in NTFS, but we'll just turn them off for a second, and turning off the columns just because the column table is a bit wide, then we can see this is the fully qualified domain name of the machine that was affected. And then over here we can see additional 2 locations where this dbutil file existed, which are not the same as the ones in the advisory. So again, we're seeing that file in different places. And we're only doing this because we've just done an exhaustive search of the MFT, of the master file table, using an Ntfs analysis. This is a pretty typical forensic analysis, but normally it takes a long time to do in a traditional way, because we would have to download the entire MFT from the endpoint, which is usually about 400 or 500 megabytes per endpoint. And then we would have to do offline processing, and this is a traditional approach. But with Velociraptor, because we're able to do the forensic analysis straight on the endpoint, then we can scale that up and do this kind of analysis in literally minutes. All right, so that was pretty cool. We've discovered 2 additional locations where dbutils was found. But now the question is, did the file exist in the past? Like what happened if the file was brought onto the system and then the attacker has somehow deleted that file or removed it? So again, let's have a look at some of the artifacts, the digital forensic artifacts that are used to determine this kind of activity. Now, usually, the USN journal is a really good source of evidence for that. Now, I'm not going to go into huge detail about the USN journal, other than to say that it's just a particular file in NTFS, inside the NTFS volume, that essentially records a running journal of all file system changes that occur to the file system. So every time a file is changed on the file system, the journal gets another record appended to the end on this side. And so it just keeps writing it that way. And then NTFS occasionally removes records from the beginning of the file, making the file sparse. So this is kind of how it works. It's got a particular location and so on. But it is a very powerful technique. It's a very powerful source of digital forensic evidence, because it tells us when a file was modified. The typical size of an NTFS USN journal is only 30 or 4 megabytes. This is the size that's actually valid, because as it gets written on this side, it gets kind of deleted a little bit over here. That sparse hole kind of grows. So again, you're just getting a quick 2-minute overview to what a USN journal is, but that's really all we need, because right now what we need to do is simply create another hunt and search for recent USN activity. So this is our new hunt. So all we have to do for that is simply search for the USN capability. And there's a USN artifact right here. And the USN artifact allows us to, configure some parameters. Let's have a look at what they are. We can simply filter for this dbutil.sys to see what, whether this file occurs in the USN file system journal. So all we do is we just launch it as normal, and then we just start it as we did before. And the same thing happens. Off we go. We're now starting to start hunting across all our 2000 endpoints. Usually it takes, again, maybe 1 or 2 minutes to actually scan the USN journal on a machine. So it doesn't take too long. And hopefully we'll find some evidence of that file being present or manipulated on the endpoints. So the nice thing about the USN journal is that it actually tells us when the file was modified in the past, because even if the file is removed from the MFD or from the disk, we still see the evidence of the file having been created or deleted or manipulated. So see that now the clients are starting to come back. So let's go and have a look at some of the results in the notebook. Okay, and look at this very cool thing. We can actually see a whole bunch of operations on different paths over here that simply occur. That we can tell when the file was created, and we can tell when the file was being interacted with or modified. And then finally, down here, we can see on the desktop, there was actually also a file on the desktop. We can see that the file was created at this time, and then very shortly after, it was deleted. So we have a deleted record on this desktop. So the desktop, remember that before we did not see that file, that it present in the desktop, but it actually, this particular example shows the file was there and it was deleted. So that is really cool about the USN, because you can use the USN to give you information about things that have been deleted. Again, a very cool sort of forensic kind of evidence. So now we know another location for when this file was present and deleted. So that's kind of interesting. So so far we've only really been looking for that file by the file name, but if an attacker is trying to use that file to maybe load an exploit into the kernel to ring 0, they don't really have to use the same file name. They can simply have a different file name. So what if they rename the file? You see, all of our detections currently would fail because we wouldn't pick that file. It's not a very unique file name. So this is where we need to kind of think about doing some custom VQL. And this is really the cool thing about Velociraptor, is that we can customize and we can create new detections to respond to new kinds of ideas. So, so let's try the hash. What if we calculate the hash? So we can do some research and we can find what is the hash of this dbutil.sys file, and then we can try and hunt for the hash. So in order to do this, we can write our own query, and I'm just going to show you this this screenshot as an example of such a query, where we simply do parse the MFT, and then we just simply compare for that file size, which we know what it is, and check the hash is correct. So in order to get this to actually work, then we can simply create, when we do this, we can actually check and see where other files can exist. So this is the query. We can come up with a query, but in order to hunt for it, then we need to take that query and run it everywhere. And the way the Velociraptor uses a query is by creating an artifact. Just a quick note about performance. When we're doing a query like this, you might know that, of course, doing a hash is an expensive operation because you have to read all the data in the file and hash it. So generally speaking, if we said something like, just hash every file on disk and look for this hash, this would be insanely slow, right? Because we will have to hash every single file on the disk. It's just not practical. So what we're doing in this query is that we're actually saying, well, this is the file size of the file. We know that's the file size. So let's compare on the file size first, and then if it matches, then hash it. Now that is extremely fast, and VQL is lazy in the evaluation order, so it actually optimizes that and does this comparison first, and then it does this comparison just because of the order, right? So it goes left to right, right? So it's not that smart, but by doing that, then it basically avoids the need to hash every file on disk, and it only really hashes the files that have exactly this size, right? So if you can provide a size in addition to the hash, then it is actually very fast to search the disk for it. So let's have a look at what an artifact is. So Velociraptor uses an artifact in order to convey and encapsulate the VQL query. So they're just simple YAML files, and they include human descriptions. We've already seen those before. And all they do is just package the VQL queries into something that's usable. So let me just show you what an artifact looks like. So this is the custom artifact. So I'm just going to copy it from here, and I'll add an artifact. And I'll add an artifact here. So if I go to the artifact view screen and just select the plus button, that creates a new artifact. And just to save on time, I'm just going to paste the artifact from before. So this is the artifact. It's going to be, it's going to have a name, some descriptions, and then I'm going to allow the user to tweak these parameters if needed. But essentially that query just gets put straight in here, and that's really all that's needed, right? So that creates this new artifact. And now you see that it just appears in the list of this one that I just added, just appears in the list of artifacts that I've just had. So again, I can just hunt for that, and I can simply say, find dbutils using the hash. So now, just like I could choose any of the artifacts before, but now my custom artifact is a choice, and it's just completely the same as any of the other artifacts. There's no differences. I can change the parameters if I wanted to, but they're exactly right because I've written the artifact. So the parameters take the correct default. So all I have to do is simply launch it and start this hunt as before. Now it's going to take a couple of minutes because it's again has to scan the entire file system as before, but it's still scanning the MFT. But now it's not actually looking for a name, but it has a much more complex and much more precise kind of match based on the characteristic of the file, just to match the size and the hash of the file. So again, it might take a couple of minutes to do that. While it does this, I will just go through these slides again. So just to remind you, again, I created a hunt using this new artifact that I've just created, and simply selected that in the artifact selection screen, and then schedule the hunt, and it's scheduled on all these endpoints, and the clients are finished. The finished clients are accumulating. Here we go. So we're getting some results coming back right now, and as the results are coming back, then we can maybe already start to post-process them. So we can see some of the results are coming back already. And now we are seeing a couple of other very interesting locations with a completely different name. So you see this one is called nothingtosee.sys, and that is in the users/mic home directory. But it is actually the same file. It's just got a different name. So the file size is exactly right. And then if we scroll over to the hash, then the hash is correct. These are all the hashes that are correct. So this type of query can find files that are renamed, but it's actually the same file because the file content is the same. So the hash is correct. So this is actually pretty cool. Okay, let me just, so this is a pretty cool thing. So let's say the threat here is an attacker is trying to use that as a method of getting into the kernel. And the reason that they need that vulnerable driver is because it's signed, so they can load it into the kernel, and then they can exploit it in order to get into ring 0 and inject their code into ring 0, so they can bring it as part of the exploit. But the interesting thing about hunting by hash is it's actually a pretty poor indicator, because hashes are generally a poor indicator. They can easily be changed. All you have to do is change a byte in the file, and that hash is completely different. So you know, if an attacker wanted us to prevent us from finding the file by hash, then all they'd have to do is change a byte in the file, and we would not recognize that file anymore. Now, they're still going to need to load the driver, right? So the digital signature still has to be correct. They can't change the file so the digital signature is not valid anymore. But the problem is that in Windows, the Authenticode digital signature scheme is not robust. It does not cover the entire file. It only covers the PE sections. Some of the file is checksummed, not all the file. So that means that there's always places in the file that you can change, that the hash of the file will change, but the signature remains valid. And this is actually kind of a little bit surprising to a lot of people, but it's not actually. It's just a weakness in Authenticode, because Authenticode is just checking the digital signature of the file, so the executable parts of the file cannot change. But there are lots of other areas in the file which are not executable, so the hash can change. Here, as you can see here, I have the dbutil.sys binary here, and I created another copy over here, and I changed one byte, and as you can see, the hash is completely different for this one, and the signature is still perfectly valid, and it can be loaded as a driver. So Windows will load it happily, but the hash will be incorrect. So searching by hash is not a great idea. It's not very good. So how are we going to detect that file using a better indicator? So what we need to do is find something in the file that is covered by the signature, so cannot actually be changed. Maybe part of the executable of the file, or the executable content of the file, which Authenticode does cover. And then if we actually go and use that as the method of identifying the file, then it's a more robust technique. So here's an example. So over here, what I did is I actually looked at a couple of VQL plugins that give me a bit more information about the file. I can parse the PE file, so it gives me information about the PE header and various properties of the PE file. And as you can see here, I've got a pretty solid PDB string, which is the debugging information for this driver. I actually have a pretty strong string here, and it is covered. This part is covered by Authenticode, so you cannot change that without invalidating the signature of the file. So I can search for that PDB file string. Also, I could search for the import table hash, or I can even search for the Authenticode, the actual Authenticode signature, which tells me who signed it and a timestamp when it was signed. So these are all very unique things that cannot actually be changed very easily with the file, whereas a hash can be changed very easily. So over here, I've written another artifact to search for it. I'm not going to go into a huge amount of detail about it, but essentially just it just searches the MFT as normal, but now it applies extra checks to do with the PE info, with the PE header and the Authenticode information. So same thing, I'm going to go over here, create a new artifact, then paste the one that I had from before, and it's going to search for this PDB string for this information, and match on subject name Dell. So it's signed by Dell. So I'm going to do the same thing, and now I'm going to say find dbutil using PDB string. Okay, and again, I simply look for this artifact that I've just created. So I'm going to use that one. I can configure the parameters, but that looks good. So just again, launch it, start the hunt, and it will start off scheduling it on all the endpoints. So it goes off and does its thing. And while it goes off and does its thing, I will just go through here. And okay. Yeah, so hunting by hash is weak. We created this artifact and we're going to go and hunt for it everywhere. So we're just doing a big hunt, and that should find some interesting hits. It's going to take another few seconds. And it may, so this will actually find files that have a different hash, because we're no longer searching by hash, and perhaps a different file name, but it is actually the same driver. So let's hopefully we'll find something. So take a couple of minutes. Okay. So while it's doing that, we could take a look at this query again. And as you can see, we are parsing the MFT as before. We are filtering for sys files only. And then those sys files, we are looking at the PE header. We're parsing the PE header, parsing the authenticode header, and then we're checking to see that the file starts with MZ header, so it's safe to parse the PE header. And again, this kind of lazy behavior is happening here, where VQL checks this first condition, and if that's true, then it checks the second condition, and if that's true, then it checks the third condition. So for instance, authenticode verification, signature verification is very CPU expensive. So we'd rather do that last after all the other things have passed the check. So let's take a look at the hits, and then we can see actually a new file that was created here, which has a different file name. And as you can see, the hash here is completely different to the hash that we were familiar with from before. So this is an example of a file of the same sys file that was modified. So its hash is different, but the file name is different as well. But when you look at the actual structure of the P header, it's the same. So this structure cannot be changed without modifying the signature. And you can see here the authenticode signature is still valid, and the file is still trusted, so it can actually be still loaded as a driver, but we can detect it. All right, so that's kind of cool. So then the next question we have to ask once we find this kind of malicious file, potentially malicious file on our endpoint, is, was it actually loaded? Did we actually have that? Did someone use this, or did they just drop it there in case, or were they actually loading it? So one of the things that we need to know is, here's an example of how one would actually load it. And then usually when you load a kernel driver, you create a service and you can start it. So that becomes loaded. And this is the command to actually create and load that service. So, let's have a look and see whether the driver is loaded. Now there is a WMI interface that we can use to ask the system about all the loaded drivers. So in this case, what we're going to do is write some VQL to call WMI and get information about all the drivers that are loaded outside of the system32 directories. This is kind of unusual, right? Normally drivers are loaded from within the Windows system32 directory. And if a driver is loaded from outside of that directory, that's a little bit suspicious. So let's write an artifact that allows us to check for that. And then what we can do is we can also hash the files and parse the P header of those files that are loaded from outside the system32 directory. So I have another query over here that I can use for this. And I actually can, I actually can actually launch that directly on the endpoint as well without having an artifact. So this is an interface that allows me to run arbitrary shell commands on the endpoint. And in this case, I'm going to run it on one endpoint. Just to show you, this is the query that I'm going to run. And let's take a look. So when I launch it on the endpoint, okay, then it basically can return some data, or maybe it's not loaded. So let me just load that. It's already running. Okay, so let me just run it as an artifact. Actually, it's probably. Yep. Okay, and then I can create an artifact out of that query. So the same thing, I've just got an artifact here. And what this does is it hashes all the loaded drivers that are loaded from outside the system32 directory. So I'll just add this new artifact with this query, store it, and then I'll create another hunt. And what I'm going to do is hunt for drivers loaded outside the system32 directory. Okay, and this one. Yep. Yeah, so we're querying system32 drivers, and we are excluding all the drivers that are outside the system32 directory. Yep. So let's create a hunt. Start it as before. This one is going to be quite a bit quicker. Should only take a few seconds. It's just a quick WMI direct filter. So let's take a look at the data. Okay, as the results are still coming in. Okay, cool. And right now we've got one hit in this network, and again we have that driver, which was the driver a clean file.sys, which was really the dbutils.sys. That is the one with the modified hash. And so we can positively identify that is actually the malicious driver. And it is actually loaded right now, and it's running right now. And it's actually loaded from user's mic, so it's not from Windows System 32. So it's an unusual location as well. So this identifies that that driver is now running and loaded. Okay, so when was the driver loaded? So we know it's loaded, but when was it actually inserted, right? It's possible to, well, we can assume that maybe the file modification time had something to do with it, but usually we can tell when drivers were loaded by looking at the event log, the Windows event log. And so you can actually open the Windows event log, and a lot of EDRs, and monitoring tools will forward these event logs off the system to a SIEM or something like that. But this is really all you kind of get out of it. It just says a service was installed in the system, and it tells you where it came from, the file. But that's about it, because so this is really not a lot of information. We really have no idea, but looking at just the event log, whether this was the malicious file or not. We just don't know, because the file name could be different, the location could be different, and we really just don't know enough context around it. So even if you're looking at a SIEM and getting this kind of event come back, and you're like, I just don't know enough about this, I really need to go and find this file. But by the time this file, so I really need to grab this file. So we have another artifact that searches for so it basically scans the event log for the system event log for that particular event ID, and it looks for and then it also parses the driver image that was loaded as parses at the PE file, so we can positively identify it and calculate hashes and things like that. So let's add that artifact in as well. So create the artifact, paste. Okay, so this particular artifact, it searches for it parses the event log file and just looks at this particular event ID, which is the one that specifies when event kernel driver loads. All right, so let's search for that. Okay, and that tells us when the kernel driver is loaded. Okay, so let's start this hunt again. Okay, and again, the same sort of process. It just schedules all the clients and runs the collection. And but what it actually will do is it parses the event log on the endpoint itself, and then when it sees an kernel driver insertion event, then it goes ahead and looks at the file on disk immediately and populates it with the hash. So we're actually getting enrichment here that we just couldn't get by the event log itself, right? So if we look at the event log, then all we're going to get from the event log is just the event data. So it will tell us that a driver was loaded, right? But we don't know anything about it. With this Velociraptor artifact, then it goes ahead and tells us, where the drivers actually exist, right? And so we should be able to find our driver here. So this is where we do a little bit of post-processing. We can simply add another condition where to see when this event data, so this is going to look at this field here, dot image path matches a clean file, right? So this will basically post-process the results of the hunt, but we seem to have got quite a lot more results. Okay, it's going to take a couple of seconds. There we go. And so we can see our file was loaded. But the most important thing from this artifact is the timestamp in event log when the actual file was loaded. And of course, we can do this processing and search for the PE info actually, or the imp hash or something like that. We can see where that file was loaded everywhere in the network and so on. Yeah, so we can see that this file was loaded several times as a driver. Yeah, the driver was loaded multiple times. So each of those is actually an event log in the event log file. Okay, so this is very interesting. We only really kind of touched the tip of the iceberg of the capabilities that Velociraptor gives us, but you can see that that Velociraptor has, by having this kind of ability to analyze and extract forensic artifacts from the endpoint, we can get a lot more coverage and much better response capabilities. There's a lot more that we haven't been able to cover, from event logs, ETW, WMI, PowerShell integration, monitoring and detection. There are many features that we haven't even touched on, but hopefully this talk gives you a little bit of a taste as to how you can use Velociraptor to dynamically, proactively hunt for threats in your environment within minutes. I mean, the idea here is to go from an advisory to a detection and remediation in minutes. That's really kind of the pinnacle of Velociraptor, the whole point of it. So we only just scratched the surface. I'd like to encourage you all to check out the following links. We have our GitHub page. We have a Discord where you can just come on and chat with us, or send us any questions or any ideas or suggestions or feedback to our mailing list. So thank you very much for listening. Thanks.